All right. Good afternoon, everyone. So, yes, as Holger said, I will be talking about this topic that we have been investigating for a couple of years now in my group at KAUST. So I'm leading the stochastic process group at KAUST, and our main focus is basically doing spatial statistics and random field modeling based on stochastic PDs. And that will also be sort of part of what I'll be talking about today. But the general kind of setup that we have in spatial statistics is often that you have some kind of spatial data. Like here we have the measurements of pedestrian counts at different parts in cities that you might want to model somehow. And the classical way of doing this is to have a latent Gaussian model where you, for instance, have in this case, you have count data, so you might have a Poisson likelihood, and then you model the mean of that Poisson distribution through a Gaussian process. And one of the kind of most well-known and most used models to use for this Gaussian process are these Gaussian Matern fields. So these are Gaussian process where the covariance function is specified to be of this form here. So this is a popular choice because you essentially have parameters that directly control the most important aspects of the process. You have a parameter controlling the correlation range, kappa, you have the variance, sigma, and you have a parameter that controls the sample patch regularity, so the differentiability of the process. So this is very well known and well used, but there are some well-known problems also with this approach in specifying Gaussian processes through covariance functions. So essentially the main issue is that they are very difficult to extend beyond this classical setting of having a Gaussian process on RD. So if you want, for instance, non-stationary models where some of these parameters are allowed to or should vary with space, this is tricky to do, to define non-stationary covariance models. You can also have more complicated spatial domains, as I will be talking about today, but you can also have other domains like on the sphere and or on the brain or other kind of manifold settings where you might want to still use Gaussian processes. And also non-Gaussian models. And then the second issue is that even for the simple stationary Gaussian process on RD, these scale very poorly with the number of observations. So essentially, computational cost scales cubically with like for doing inference or prediction, and storage cost scales quadratically, which essentially means that you cannot really scale this to big data applications. So a popular approach to deal with this is the so-called SPD approach. This is based on a well-known fact that this Gaussian process with these Matern covariance functions, if you look at those on RD, they can actually be viewed as solutions to this fractional order stochastic PD. So W here on the right-hand side is white noise, and kappa is the same spatial range parameter as in the covariance function. The fractional power out there in the operator is linked to the smoothness parameter mu that we had for the covariance function, and delta is the Laplacian. So this has been known for since the early 60s when Peter Whittle showed this, but it wasn't really much used for anything until this important paper in 2011 where Lindgren, Ruge, and Lindström proposed to use this representation to come up with computationally efficient Gaussian Markov random field approximations of this process. And the idea is actually simple. So basically, the idea is that instead of working with the covariance-based representation, we will instead take this PD representation and we will discretize this using kind of well-known finite element methods. So what that does in practice is that we do a piecewise linear approximation of the Gaussian process in terms of these phi here that are piecewise linear hat functions, the classical finite element hat functions. And then we have now transferred this continuously indexed Gaussian process to these space expansions. We are set to compute what is the distribution of the stochastic weights in this space expansion. And then it turns out that if you do this, so we compute the finite element approximation through this so-called Galerkin approach. If that smoothness parameter alpha is an integer, you obtain that the vector of these weights form a Gaussian Markov-random field. So this is a multivariate Gaussian random variable where the inverse precision matrix is sparse. And that is then what you can use for basically scaling up this to big data applications. Another advantage is actually that the computational cost will now scale with this small n, which is the number of basis functions, and not the number of observations or spatial locations. So that's also that you can also use to basically further reduce the computational cost by essentially using fewer basis functions.
So can I ask a question?
Yeah.
Is this clear how good this approximation is?
So that's another that's another advantage here, is that because this is based on finite elements, you can essentially derive convergence rates for this approximation. So yeah,
okay,
nice. So that's a nice advantage with this type of approximation compared to many other approximations that have been proposed to deal with this kind of big N problem in spatial statistics, is that here you really get sort of theoretical guarantees. So that's one thing. The other advantage with this SPD formulation is that allows us to extend the model beyond the classical RD setting. So we can, for instance, define these kind of matern-like models on more general domains, like the surface of the brain, simply by posing the same SPD on the surface of the brain instead. And then we simply define whatever the solution is to that equation, we define this as a matern field. You can also easily extend this model to non-stationarity simply by allowing the parameters to be spatially varying. And the advantage is, so if you go back here, if you, for instance, let this parameter kappa be spatially varying, if you can show that this equation still has a solution, that is automatically a solution that is a well-defined Gaussian process that has a well-defined covariance function. So you have kind of transferred the problem of defining non-stationary covariance functions to simply checking that this equation has a solution. And that's often much, much easier than going to the covariance routes. You also get some kind of physical motivation here, especially if you work with spatio-temporal extensions that I will briefly mention later, because then you have this kind of PD formulation that somehow, well, at least could be like physically inspired. And you can do non-Gaussian extensions by simply changing that driving Gaussian white noise to some non-Gaussian, and then you would still get the same covariance function, but more general marginal distributions. Right, and that is what I said. So the nice thing also is that you have like solid theoretical foundations here for numerical methods, because you can take advantage of a lot of the literature on finite elements. Good. So what I will talk about today, as I mentioned, is Gaussian random fields on metric graphs. So this is one of the cases here where we have a more complicated spatial domain where we want to define the process. And the motivation for this is that a lot of data in spatial statistics actually lives on network-like structures. So for instance, if you're modeling data on rivers, like river discharge data, or if you're modeling like risk of traffic accidents, the thing that you're modeling only lives on the network. And we want to measure then also, like if you think about correlation of the process at two locations, that correlation should be measured in terms of the distance on the network, right? Because you could have two, like one location here and one location here that are close in Euclidean distance, but they are very far in river distance. And you could have the same thing in roads, like for instance, roads, lanes in different directions might have very different traffic behavior at a certain time. So it doesn't make sense to model the correlation in terms of Euclidean distance in this case. And here we have some other examples of some classical dendritic spine data and data of classical cholera outbreak in London. That is also data that is somehow on networks. So what we want to do is to model data like this using Gaussian processes. And we want these models to be defined in continuous space. So this is not a process on a discrete graph, but we really want to define the process also on the edges of the graph so that we can do things like kriging or spatial prediction on this network. That you might want to predict what is the risk of accident at some locations where you haven't maybe seen much accidents. Right, so that's the motivation. And then the first thing we have to do is to define what we mean by this network structure. And this is what a metric graph is. So a metric graph is basically consists of the same things as a normal graph does. So we have a finite set of vertices, and we have a finite set of edges connecting these vertices. But then the difference is that now each edge is not just an abstract sort of connection, but it's a physical, it's a curve that we parameterize by arc length. You can be somewhere on this edge or on that edge. And then we equip this graph with a metric so that you can measure distances between points at different locations on the edges or at the vertices. Good. So that's the type of physical space where we now want to define a Gaussian process that lives on that. And the natural thing that you might, the first natural idea would be to do the same thing as we do in RD. So define a covariance function on the network, and then use that covariance function as the covariance function for a Gaussian process. Right, so you take V as the distance on the graph, and then you define an isotropic covariance function. So you take some function R and evaluate this in the distance between points, and say that this should be the covariance function of the process. Now the issue here, the big issue, is that you have to make sure that you choose this function R in such a way that this function rho is still positive definite. So otherwise it's not a valid covariance function. And the problem is that most isotropic classical covariance functions that we use in spatial statistics fail to be valid in this setting. There are some exceptions. So one case where you can do this is that if you restrict the type of graph you look at to something that is said to have Euclidean edges, it doesn't really matter what that is, but it's kind of a subset of metric graphs. Then this Matern covariance that we saw before is valid if the smoothness parameter is at most a half, and if we use as the metric not the geodesic distance, but something that is known as the resistance metric. Again, it doesn't really matter exactly what that metric is, but it's essentially a distance that is inspired by electricity theory, where essentially 2 points are close if you also have many possible ways of going between them in the network. Okay, so this is one way of constructing an isotropic Gaussian process on a network. As far as I know, there are no constructions to define differentiable processes in this setup. So if you know this Matern covariance, that parameter nu So if that is equal to a half, that corresponds to an exponential covariance, which is then a Gaussian process that has continuous sample paths, but not differentiable. Another slightly annoying thing is that this restriction of having Euclidean edges is a bit artificial. So for instance, here's a graph that has Euclidean edges, whereas this one doesn't. So this works on this graph, but not on that, which is which means that actually in real applications, you're often in the case where the graph does not fall into this subclass of Euclidean edges, and then you cannot really use this.
Quick question.
Yeah.
What goes wrong on the right-hand side?
Well, I mean, so one of the requirements for having Euclidean edges is that two vertices, if they are connected by two edges, these edges must have the same length. So here you see you have two edges of different lengths that connect them, and then somehow, yeah, that doesn't satisfy this.
So just to understand that, would Euclidean mean I find a repositioning of the vertices in some RD so that there are direct lines to this, direct links, and triangularity and so on? Or what does Euclidean imply?
No, so it's not really like that. So Euclidean, I don't actually know why it's said. I actually don't know why they chose this name of Euclidean edges. But there are like three requirements that you must have. The first is what I have said, that you cannot have two edges of different lengths that connects two vertices. The second, which is more problematic actually, is that any two vertices, the shortest distance between any two vertices must be obtained by going through an edge. So you could imagine that you have a graph where you take two locations, and there might be a direct edge between them that is longer than the shortest path between them, and that is also not allowed. So there are some things like this that. Yes. Now, even if you are in this setting that you have a graph with Euclidean edges so that you can use this approach, a more fundamental question is actually, do you want an isotropic Gaussian process in this case? So if you think about this in spatial statistics, why do we often use isotropy? Well, we use it because it's like a nice simplifying assumption. And you often use it on RD or on S2. But it often makes sense there because basically, if you're in these spaces, they look the same everywhere. You can basically translate, you can go to a different place on the physical domain and it looks the same there. Topologically, it looks the same. This is not at all the case for metric graphs. So for instance, if you assume isotropy, the correlation between these two green points will be the same as the correlation between the field as these two red points. But you can imagine that the process might behave very differently if you think of this as rivers or something. If you measure correlation along the same river segments, that should sort of be higher than if you take two locations at different forks of a river or something. So I would argue that isotropy is actually often not a realistic assumption in many applications in this case. Okay, so what do we do instead then? So the main goals we had when we started looking at this was basically to create some general class of spatial and spatio-temporal processes that we can also make differentiable. And we wanted to do this in such a way that we still can do like have efficient methods for actually using these for statistical applications. And then kind of on the way to doing this, we realized that there were some more fundamental issues that we had to solve on the way. So for instance, look at Markov properties for fields on domains like this. And yeah, some other things. And then finally, the final and maybe most important goal was that we also wanted to define or introduce a software package for actually using these models that we define so that you can use this for data analysis. And now the starting point for all this was to extend this SPD approach to the graph setting. So this is sort of the, having this background on SPDs, this was the natural starting point to define a Gaussian process as a solution to a stochastic PD on this metric graph. Right, so this is kind of this would be then, if you post this equation on the metric graph, then this would be what we define as a Matern field or Whittle Matern field. So this is not so difficult to like defining Gaussian white noise. That's easy to do on this domain. The issue is that what do we mean by the Laplacian on a network? Because on RD, the Laplacian is just the sum of the second partial derivatives. But now in this case, if you're on an edge, then the Laplacian, you naturally define it just as the second derivative on the edge. But then you have these intersections, like where the edges meet, and there you have to actually make a choice of how do you define the operator, like at the boundaries or at the vertices. Fortunately, this is something that people have thought about in the physics literature, and a common choice is the so-called Kirchhoff conditions. So this is like boundary conditions that you pose that says that essentially, well, in this case, if you would pose Kirchhoff conditions, you would require that the solution is continuous and it has this sum to zero constraint on the partial derivatives at each going out from every vertex. So this essentially is some flow zero condition out or in of a vertex. And this is actually a natural generalization of Neumann boundary conditions. So if you have a vertex of degree 1, just like the endpoint of an edge, this just translates to having a Neumann boundary condition, so zero derivative at the boundary. Good, so that's what we started using. So we will use this delta gamma as the Laplacian equipped with these vertex conditions. And what this specifically then means is that, so this is a differential operator, and we impose these boundary conditions by specifying the domain of this operator. So the domain of this operator are the functions which are twice differentiable on the edges. They satisfy these Kirchhoff conditions, the sum to zero constraints, and they are continuous.
I think it's a stupid question. Is this always clear that there exists a solution and it's zero?
No. So that's something you have to show them.
Oh,
exactly.
okay.
No, so exactly. So that's the next thing. So
Okay.
so having defined this operator, we can now define the shifted Kirchhoff Laplacian, and we can then define. So then we will define these Whittle Matern fields. So if they exist as the solution to this fractional order equation. And now, actually, it is not difficult to show that this has a unique solution because there's actually quite a lot known about this Kirchhoff Laplacian. So we have kind of control over the eigenfunctions and eigenvalues of this operator. So it's actually easy to show that as long as this fractional smoothness parameter alpha is more than a half, then we have a unique solution, which is a Gaussian process, like a L2 Gaussian process, meaning that it has pointwise smoothing. If alpha is less than a half, you actually still have a unique solution, but it's not a function as a solution. So then you would have a functional as a solution. Right, so the solution is just a centered Gaussian process, and it has some covariance function that we will call rho. Good. So we can actually say quite a bit more about these solutions simply than that they exist. So one important property is that, so what this proposition is saying is essentially that if you define the process on this graph or that graph, it will be the same Gaussian process. So you can add or remove vertices of degree 2 without changing the model. And this will turn out to be very useful later for statistical inference, because it essentially means that you can add a vertex at any observation location. And then you can do that without changing the model. We can also say something about sample path regularity. So essentially, this parameter alpha, as for the Matern fields in RD, it will control the regularity of the solutions. So it specifically controls the Hölder regularity of the sample paths. And if this alpha becomes big enough, you start to get differentiable and twice differentiable and so forth sample paths. Yeah, that's exactly what this is saying. Right, so here you have two examples of this. So this is on a simple graph with just four edges and 4 vertices. So in the top here, I'm showing the covariance function, or specifically the covariance of the process at this point with all other points in the graph. So this for alpha 1 and for alpha 2. That's how the covariance functions look like. And here, down here, you see corresponding realizations, and kind of visually, you sort of see that if for the alpha 2 case, this looks sort of smoother than the alpha 1 case. Good. So then we can also say more statistical provide more statistical properties of these models as well. So one important thing for if you study sort of asymptotic theory for likelihood estimation, one of the ways of showing that you can actually estimate parameters is by going through Gaussian measures. So what this theorem is saying is essentially that if you don't know what a Gaussian measure is, no worries. But essentially for any Gaussian process induces a Gaussian measure. So if you take two of these Whittle-Matern fields with different parameters, say the first one has this kappa tau alpha and the other one has, well, the same tildes, some different parameters, then the corresponding Gaussian measures are equivalent if and only if they share the smoothness parameters and the tau parameters. This directly tells us that this range parameter kappa does not change the measure, kind of. So that tells you directly that you will not be able to estimate that parameter consistently under infill asymptotics. So that is what this proposition is saying, that essentially you can estimate, say, this parameter tau consistently if you get more data on the metric graph, but you cannot estimate kappa. This maybe looks a bit bad. However, this is exactly the same thing as what happens with Matern fields on RD. They have the same property that you cannot estimate the range consistently. Now, why this is not a big deal is because if you use these models for prediction, it turns out that you get asymptotically optimal predictions, even if you misspecify the parameters. So as you get more data, essentially, if you want to use this model for prediction, the only parameter that really is important to specify correctly is the smoothness parameter. So that's essentially motivates why it doesn't really matter so much that you cannot estimate the range so well, because that doesn't matter so much for predictive purposes. Good. So those were some kind of theoretical properties of these models. So we have now implemented these in a big R package called metric graph that contains a lot of functionality for dealing with data on networks, and also that implements these Whittle-Matern fields. And this package also has interfaces to, for instance, these R-inline, InLabRu software packages, which are popular software packages for doing Bayesian inference. So what this means in practice is that you can now define a model on a network using this metric graph package, and then you can do full Bayesian inference for it using these packages. So just to kind of show you how it works. So here's a small illustration or a small application. So here we have some traffic speed data from San Jose in California. So here's the highway network in San Jose, and if you, the dots here are the locations of traffic cameras where they measure traffic speed. And this looks like a quite simple network, but if you zoom in, you see that we have basically edges for all the lanes in the network. So you have a quite tricky network structure, even though it looks kind of simple when you zoom out. So here is actually the entire code for fitting a model to this data using these packages. So you start by defining the graph. You add observations to it. You define this Whittle-Matern model. In this case, we fix the smoothness parameter to 1. And then we fit it using, in this case, InLabRu. We extract the results. And here are the estimates then of essentially the standard deviation and the practical correlation range of this process. You can then also use it for kriging or for spatial prediction. So here we define a mesh on the network where you want to predict the traffic speed, and then you predict. So here you see then a kriging prediction of the traffic speed on the network. And this, I think, is a good example to illustrate why we do not want to use Euclidean distance to model data like this, because you see that in this case you have very low speeds in one direction on the highway, but you have much higher speeds on the other direction. So it would be very bad to say that, for instance, these two locations, they are very close in Euclidean distance, but they are very far in highway distance, and they have very different values. All right. Yeah.
So this data is somehow at the average speed at 1 day, or?
So here it is the average speed at 5 p.m. Like with a 30-minute interval. That's something like this. Yeah. Good. So the last thing that I haven't told you now is what does this actually do? Like I told you some properties of the models, but I did not tell you still, for instance, how do you evaluate the likelihood of this model, or how can you actually use this for statistical inference? So to explain that, the first thing we have to understand are the Markov properties of these models. So this is the general definition of what we mean by a Markov process on a metric graph. Now, what this in practice essentially means is that if you take the process at this green part and the black part, they would be conditionally independent given the values at the red part, right? So it's essentially the same idea as Markov properties in time, where the past and the future are conditionally independent given the present. Right, so you can formulate this more mathematically, and this is what is done here, but it's essentially that's kind of, except that you don't really now have a past or a present on a domain like this, so you have to talk about kind of separating sets. You can then also define higher order Markov properties. And this essentially, so if you have a second order Markov process, that translates essentially to that the process is still, you have conditional independence between the green and the black part, but now you have to condition on the value of the process and its derivative. So that's essentially what's if you have a pth order Markov random field, we say that it's a pth order Markov field if it has p-1 derivatives, and if you condition on the value of the process and the derivative, then you get this conditional independence. And it turns out that for these Whittle-Matern fields, they are Gaussian Markov random field of order alpha if and only if alpha is an integer. So this smoothness parameter, if that takes integer values, that gives you this Markov property. And this is then what we can use to actually evaluate likelihoods. Now, so how do you then use that? Well, the issue is that if you just take the stochastic PD representation directly, you don't really know, like, okay, how do you evaluate the likelihood of a stochastic PD? So what we will instead do is to come up with a different representation that is easier to evaluate, but that's just a different way of representing the solution. And the idea is as follows. So we will define some independent Gaussian processes on each edge in such a way that after you condition on that these should satisfy these Kirchhoff vertex conditions, then you get the solution to the stochastic PD. And this essentially is possible because of that Markov property. Now, the reason for why this makes it easier is because that means that you can view this U as a Gaussian Markov random field under linear constraints, where this linear constraints is giving you this tying together thing. And this is something that is well known how to deal with in statistics. Right, so you can evaluate if you can represent the process as a Gaussian Markov random field under linear constraints. We essentially know how to deal with that. And for instance, for alpha equal to 1, you can actually use this representation to get an explicit expression for the precision matrix of the process, so the inverse covariance matrix at the vertices. And it looks like this. It doesn't really matter what it is, but the important thing here is that this is a very sparse matrix. And also, because now we can add vertices or remove vertices of degree 2, this fact that you can evaluate the distribution of the process at the vertices, now combining that with the fact that you can add vertices for where you have observation locations, means that you can evaluate the likelihood of the model. So this is basically what is implemented in this package. So just briefly, two more general results about this Markov property that I find a bit interesting. The first one that we realized when we were dealing with this is essentially, so what this theorem is telling you is that if you have a graph, a domain, that contains a cycle, so that you have some vertex that has you have a way of going along the network and ending up in the same vertex again. But it's not only a cycle, so it's not just a circle. In this case, there is no Gaussian process that is Markov and isotropic, which is a very interesting result, I think. So this means that in practice, you have to choose between Markovianity or isotropy. Another thing is that you might wonder about is if you have this model, a Gaussian process now that has this Markov property on this general metric graph, if you restrict this to some observation locations and you only look at the process there, you would kind of expect that you should get the graphical model, so a discrete Gaussian process on a discrete domain. And this is basically what this result is saying, that you indeed do get a Gaussian graphical model where essentially the dependence graph of this graphical model coincides with the metric graph. Good. So the next thing, or the last thing, is then to say something about more general models. So now we have basically defined a class of models that is corresponding to these Matern fields, like stationary Matern fields. But you can actually do more. So for instance, if you want to define non-stationary models, as I mentioned before, you can basically allow the parameters of the model to be spatially varying. And you can do the same on the graph. So you can essentially take this differential operator and look at a more general differential operator that has some spatially varying parameters. And essentially, if you do that, you can basically show the same type of results as for the Whittle-Matern fields. So if you have a differential operator like this, then we call the solution a generalized Whittle-Matern field, and the existence and regularity of the solutions follow essentially in the same way. And also under some mild regularity conditions on the parameters, you still get that these are Markov if and only if this smoothest parameter is an integer. Now the difference to these generalized models is that we do not, at least yet, know how to do inference for them exactly. So we do not know how to evaluate the likelihood of such a model exactly. So in this case, what we can do is to do finite element discretizations, as was done in the original SPD approach. So that's exactly what we do. So we come up with a piecewise linear approximation of these processes, and in terms of these head functions on the network, and then we can compute an approximation like that. And the nice thing is that even if you have this fractional operator, we can still handle that and get a computable approximation where we actually have control over the convergence rate of this approximation in terms of essentially the mesh for the finite element approximation. So these types of models are also implemented. We have a second kind of big R package that we are maintaining in our group at Gauss called RSPD that contains a lot of implementations for these kind of fractional order stochastic PDs in statistics. And in particular, you can use this package in combination with this metric graph package to analyze these generalized Whittle-Matern fields. And you still have interfaces to these Bayesian software packages so that you can actually use these models for inference. So here is just, again, some code to show you how to actually fit one of these generalized Whittle-Matern, or well, in this case, fit the Whittle-Matern field, but with a general smoothness parameter, so that a model that is not necessarily Markov. So then the code looks similar. You just now have to define a mesh. So the mesh for these head functions. Then we define the model and we fit it in the same way. And you can see that in this case, this here nu. So this is the estimate of nu. So the posterior mean of that parameter is about 1.48. And you also get credible intervals for it. And in this case, nu equal to 1.5 corresponds to a smoothness of alpha equal to 2, which is what we used before. So in this case, it seems like a Markov model of order 2 is actually a good model for this data. Because when you estimate the smoothness, you get something that is almost an integer. So okay, so just quickly, some other things. I will just give a few kind of commercial of other things that you can use these models for. So a very natural thing to use models like this for is to look at point pattern data. So if you have like locations of traffic accidents, for instance, a natural thing to do is to use a log Gaussian Cox process to analyze those. And this is something you can define essentially because that is a Cox process where the intensity is a Gaussian process. So now you can just take the intensity as one of these Whittle-Matern fields on the metric graph. And that's also something you can do using this package. Here's just one result of one such application where we looked at traffic accidents in a city in Saudi Arabia. And what this is showing is essentially like a hotspot analysis of where you have kind of dangerous parts in the road networks. Another thing that we are actually currently investigating is to come up with spatio-temporal extensions. So what if you have space-time data? And then it's natural to look at like space-time versions of this SPD, where you also have time now in the equation. So this is sort of like a fractional heat equation. What this what makes this challenging is actually that often when you think about space-time data on networks, you often want to have drift in the data. If you think about rivers, like there's a river, yeah, there's a water flow direction that basically tells you that you want to have some kind of advection component in the equation. So that is why we have this advection term here, and that is also what makes it a bit more challenging to analyze theoretically. Good. So, but yeah. So summary, basically, so this what we have done so far on this topic is to construct big class of Gaussian process that actually can be defined on general compact metric graphs, and where you can actually have differentiability. We have known sample path properties and statistical properties of these models. And in the Markov cases, so in this, when you have this integer smoothness, you can actually do exact inference for these models. In the more general cases, we have to rely on finite element approximations so far, but at least we have some kind of theoretical guarantees for those approximations. And we have this metric graph package to, so if you have some data on networks and you want to try this out, you can try using this metric graph package, and you don't really need to know the theoretical details behind these models to actually use them. Yes. So, however, so this field is quite young and there's still a lot to do. So some things that we are thinking about and working on currently are, for instance, more general spatio-temporal models. Gaussian free fields is something that is of importance in probability theory. Non-Gaussian versions of these models. Also, we're looking at links to causal models. So this is like causality. If you have this graph structure, it's natural to think about causality, and that's also something you could think about in this case. More specific advection-driven models for rivers, when you have this kind of water flow, having these Whittle-Matern fields might actually, you might think about actually other PD type models that might be more suitable in those cases. Yeah, and applications is also something that we are currently would like to do more of. Good. So yeah, so I think in conclusions, I've tried to kind of give you an overview of the type of work that we are doing in this field, and I think it's a very exciting new field of research. Both because there is a lot of fundamental results that are missing, but at the same time, you have really clear applications. So it's very easy to go essentially from all the way from theory to applications. Good. So if you want to see, well, if you want to know some details of anything I talked about, I think these are the papers that this is based on. And that's it.
Thank you very much.